Hey there! Turn on your speakers. Do you have finals week coming up? Projects due? Homeworks are piling up? Are you freaking out that you're getting boxed in with deadlines? Here's an idea. Get help. Think Geek Exams. Find us on Facebook, Twitter, or YouTube.
Hi, so this is Statics11.4 homework, and this homework is pretty similar to 11.3, where we also had a ball, socket, bar, and strings, but this one is slightly different. Let's look at what is different here. So in the previous one, we had the ball socket at the origin O, but this one, the ball socket is raised to point A, which is in the z-axis, 0, 0, 8 coordinates. And we have, pretty similar to the last time, we have coordinates for each of these points. A is the new one, then C is the other end of the bar, which is on the x-axis, and then D and E are the string, the Harseners. Basically they're fastened here, D and E, and B is the midpoint where force F is being applied, midpoint of AC where force is being applied in the downward direction, and the force is minus 1165 pounds. So previous one was in newtons, this one is in pounds, so that's not a big deal. So we are asked for, just like the last time, we are asked for the tension in the strings over here in CE and CD directions. And also we're asked for the reaction force at A, and we are asked for the coordinates for them, so AX, AY, and AZ. So moving on. What we know is the points A, C, D, and E, and B can be calculated as the midpoint of A and C, so that's pretty simple. We need RAC, which is the distance vector from A to C, and we can get that by subtracting C from A, and we also need RAB, which is a distance vector from A to B. These vectors, we need them for calculating the moments about A. So A to B is basically, we can get it by subtracting B from A, and we get RAB. Those are pretty simple. Next, we need the direction vectors. The first direction vector is the easiest one. It's minus k over here, which is the direction vector for the force F. So U of F is minus k. Then we need U of CE, which is calculated here over here. We get the vector CE by doing this, and then we get the unit vector by dividing by the magnitude. And we do the same thing for CD. UCD is the direction vector that we need, unit vector. And our force magnitude is 1165, we know that. And the forces acting on the bar are F, the tension from C to E, tension from C to D, and the reaction force at A, the ball socket reaction. And only F, the vector F, is known. All right, moving on. What we are asked for, just like the last time, we were asked for TCE and TCD, and we're asked for the reaction vector. So that's pretty, reaction vector at A. So that's pretty similar to the last time. Let's get some theory out of the way. A ball and socket has a reaction moment of 0. So whatever moments are being created by these forces, the tension forces and the force F, those moments have to sum up to 0 because the ball and socket doesn't provide any moment whatsoever. So that's the first equation. We calculate the moment from about A for the tension on CD. So we do that by getting RAC cross force CD, so TCD. So that's the first term over here. Then the second one is the moment for the tension on CE. So that one we get by RAC again, crossed with tension on CE. So that's the second term over there. And then finally we have the moment for the force F. So it's acting at a distance of RAB and crossed with well, the force vector of F. We should get the third term. And if we add all three, they should equate to 0. So the way we get the useful equation is this one. What happens here is this TC over here, the vector TC can be separated into TCD, the magnitude, and UCD, the unit vector. And so we separate those out and we create a known cross multiplication that we can calculate, because all of these are known numbers. The TCD is not known. Same with TCE, we don't know that, and these are known values, so we can calculate these values. And then RAB is known and F is known, so we can calculate this as well. So only unknowns are TCE and TCD, and this is a vector equation. So it's got three equations in there, and we should be able to calculate TCD and TCE out of there. And then once we're done with the moments, we basically add up all the forces, and they should equal to 0. So the forces are, we talked about it already, there are 4 forces. The force F, which is acting downwards, the force TCD, which is acting in the D direction, and force TCE, which is acting in the CE direction, and finally the reaction force at A, which is RA. So all 4 of these should add up to 0, and from this equation we get this equation of RA, which is just taking all these terms to the right hand side and turning into a negative sign. So moving on, these are basically the calculation in Matlab. So we know that RAC is OC minus OA, so we calculate that. RAB is B minus A, we calculate that. And then UCD is basically we use CD vector, and CD vector is D minus C right there. The same with the CE vector, which is E minus C. And UCD is just CD over magnitude of CD, and that's exactly what we have over here. CD over norm of CD. Norm of CD is the Matlab version of magnitude, and that displays out our values of UCD and UCE, which we will use later. So we have calculated successfully the unit vectors. Then what we need is we need to multiply out RAC and UCD to calculate the vector coefficient that we need to multiply to TCD. So this is a vector coefficient that we're trying to calculate. RAC cross UCD is calculated over here. RAC cross UCD. And that is this number over here, and we store that over here as well. RAC cross UCE is the vector coefficient of TCE. TCE is unknown and TCD is unknown. So this vector is being multiplied to the scalar, and we calculate that in the green box over here, and we bring out the value over here, and finally the right hand side is RAB minus RAB crossed with F, and that is 4660J, and we basically have a negative sign before that, so I put that negative sign here in the purple. So we have the coefficients done, so we should be able to notice that the first row and the third row are exactly the same. First row and the third row are exactly the same. First row and the third row are exactly the same. So we can pretty much, since the first row and the third row are exactly the same, we can drop the first row altogether. So that's what we did over here. We dropped the first row and we created a vector, a matrix out of the second and the third numbers of the first two vectors, and basically that is our matrix. This is minus 4.476, that's that one, minus 3.73, that's that one, and minus 0.93, that's that one, and 3.27, that's that one. This is the vector we created, and this is the right hand side over here, and that's minus 4660 and 0. This is our the y vector that we call it. So this in Matlab we calculate the matrix A and the y vector, and then when we calculate the inverse of the matrix and multiply that with the y, we should get the tensions, the two tensions, and that's what we did over here. And the two tensions are output in Matlab over here, and those got copied over here in our PowerPoint slide. So there are two values. Those correspond to the magnitudes of the tensions in the strings. And finally, if you remember, we got this equation from the sum of the forces. All the forces got added, and that was equal to 0. So we could get RA from there by taking all the forces in the other side of the equation. So we know what F is, we know what TCD is from the previous slide, we also know what TCE is from the previous slide, and we know what the unit vectors for TCE and TCD are. So all of the values are known here. So all we need to do is basically put it in Matlab. So TCD is the first. So in here, this is a T vector, and so first element is TCD, and the second element is TCE, and RA is basically this equation right there, and that spits out our R of A, and that has 3 coordinates, so that's exactly what is needed. The 3 coordinates are put in over here in the answer box: AX, AB, AY, and AZ. And TCD and TCE are copied from here, and they all match up, and the answer is correct. So that ends our presentation for 11.4. See you guys for the next statics video.
Think Geek Exams. Our agents have Masters of Engineering degrees from MIT, Stanford, Georgia Tech, Caltech. We give you solutions to mathematics, physics, computing, and engineering. Find us on Facebook, Twitter, or YouTube.